All right, welcome to the final video for Chapter 7. The goal of this video will be to understand how mgh arises from this other formula for gravitational potential energy that we have. So there's the more general formula that's always true, U equals minus g m1 m2 over r. And then if you're, for points near the Earth's surface, that formula simplifies to a constant plus mgh. So we want to understand where that comes from. And the key to understanding that is going to be understanding the binomial series expansion. So this video will be split into three parts. The first is talking about Taylor series and deriving this formula right here. So either you've seen that in calculus before and this will be a refresher, or it'll be a preview for seeing this in like a Calc 2 class. That'll be the first part. The second part will be answering this problem using that formula. And then the third part will be doing the mgh part. So then coming back to this section in Shankar. So Shankar does this a slightly different way. We're doing it in more generality that will help you in other physics problems, because this is you're gonna see this over and over and over again in physics. You're gonna use this over and over again. Okay, so part 1 of 3, the Taylor series. Taylor series expansion. So if you have a function, it can be doing any crazy thing, right? Actually, let me draw it like this. Your function you can approximate with a series of polynomials. Okay, so pretend you're really interested in this point for whatever reason, right? So if you were going to, okay, so this graph right here is the actual function, f of x. If you were going to approximate that function to 0th order, so in other words, a 0th order polynomial, you would just choose a constant. You would choose this constant. So whatever value the function is, you would say that my approximate value for f of x, if I'm only allowed to keep 0th order terms, is this. The first order approximation, you want to choose, so in other words, we want a function that looks like f of x near these points. So we would choose a line that would look like this, right? We choose a line that goes through our point and also that has slope equal to f of x. So this would be our approximating the function near our point. So the point that we're approximating around is called x naught. So we choose a straight line that goes through f of x naught and also has slope equal to the slope of f of x at x equals x naught. So this would be the first order approximation to f of x. So you can keep doing this to whatever order. You can imagine what the parabola would look like. So the parabola would go through this point, it would have slope equal to this, and it would also have some curvature to it. So it would be true, and it would probably go closer to what the actual function looks like right there. If I was better at drawing parabolas, you can imagine a parabola that goes through that point, has slopes. The slope of the parabola is equal to the slope of f of x at that point. It would also have the same curvature. So the bendiness, the radius of curvature would be the same of the two at that point. So you can get better and better the higher order you go to in this Taylor series expansion. So there's a formula for this, for what the Taylor series looks like. So f of x is approximately equal to, so the first order term is just we would plug in x equals x naught, right? That's the best we could do. That was the straight line piece. So if we were, that's kind of bad though, right? That's only equal to this. It has nothing to do with the function other than it has that value. Remember, the next best piece was this, so the same slope. So keeping that piece is this to the first power. And you can imagine, like right here, there's a x minus x naught to the 0 power. We're gonna see the pattern of these terms. So you can imagine there's actually a x minus x naught to the 0, but this is just 1. So we didn't have to write that in there. But see how this piece is a straight line. So this is the slope of the function. And then this is keeping track of how far you are away from x naught. So when x equals x naught, of course, the straight line matches up with this constant function. But suppose you're at a point that x is a little bit bigger than x naught, so this piece would be positive, but the slope there is negative for this point that I've drawn in the figure there. And so our approximate value of f of x is going to go down by a little bit, which makes sense, right? If the slope is right here, our value is going to be a little bit less than f of x naught. Right? And it depends on how far we are away from x. So, in other words, the first derivative keeps track of that slope information. And remember, the second derivative also keeps track of the curvature. So the next term here, so this is maybe a little mysterious. There's actually a 1 over 0 factorial here and a 1 over 1 factorial here, but those just give a factor of 1. This is 1 over 2 factorial. A second derivative keeps track of curvature. The next term would be 1 over 3 factorial f, three derivatives evaluated at x equals x naught, and on and on and on. So you can see how this formula generalizes. So the more terms you include, the better you can approximate the function for points farther and farther away from your point of interest, x naught. Okay, that's the gist of Taylor series expansions. So what we want to do now is apply this. So this is in general. This is totally general. But now we're going to apply it to a very special function that appears a lot. So this one's in general, but now we're going to choose f of x equal to 1 plus x to the eighth power. So a is just some constant. So we're keeping this pretty general. So it turns out that what we do will apply even if a is not an integer. Just because this pops up so often in physics. So we'll see that this will help us answer this question about how much your weight goes down as a function of height. And it'll also be able to address this MGH thing. Okay, so, and we're going to approximate this around. Approximate around x naught equals 0. Okay, so we have in mind that x is going to be a small number here. So 1 plus a small thing, small compared to 1. And just small in absolute value. So it could be, x could be negative or positive, but the absolute value is much, much less than 1. Okay, so let's plug it into our formula and see what happens. So f of x is approximately equal to f of 0. So actually maybe what we want to do, before we plug it into this formula, we need to evaluate the derivatives. So we need f prime of x, and then we have to plug in x naught, right? See how these right here involve first derivative, second derivative, evaluated at the point that we want to expand around. So let's take some derivatives here. F prime of x is a times 1 plus x to the a minus 1. The second derivative is a times a minus 1, 1 plus x to the a minus 2. And you can imagine keep on going. And you would just get a string of like a times a minus 1 times a minus 2, etc. Okay, so f of 0, we're going to need that. So imagine just plugging in x equals 0 right here. You have 1 to the a power, that's just 1. F of 0 is 1. Looking at this one, we have f prime of 0. So we're taking f prime of x and plugging in x equals 0. It looks like it's a, and then times 1 to the a minus 1 is just 1. So this is a. F double prime 0 is a times a minus 1. Okay, so these are all the terms that we're really going to care about. And actually, I could have probably stopped here. Most of the time, we just need the first order expansion. So what the Taylor series expansion says, and actually you might hear the term in your calculus class, you might hear Maclaurin expansion. So if you're expanding about a point and x naught is equal to 0, that's called Maclaurin series. But in general, you can expand around any point. That's called Taylor series. So f of x is f of 0, which is 1. So I'm going to go ahead and say 1 plus x to the a is approximately equal to 1. So that's f of 0 plus, and then the first order term, f prime of x naught, is this. So 1 plus a, and then x minus x naught to the first power is just x to the first power, because x naught is 0 here. So plus ax plus 1/2. So the next term would be 1/2 a times a minus 1 x squared plus etc. Okay, so you know how to derive more terms here. You would know what to do if we wanted f triple prime, f, a fourth derivative of x, etc. So that would just add more and more terms here. But a lot of times we, a lot of times we just need these terms right here. And this is a valid approximation. So x has to be much less than 1, and a can't be too, a can be big as long as a times x is much less than 1. Okay, so if a times x is order 1, you start to, like if you have 1 plus a really small thing, but then you raise it to a really high power, then you start getting, like that's like the definition of e. Like if you do 1 plus 1 over a million, and then raise that to the 1/millionth power, or to the millionth power, that's about equal to 2.71828. This number e. So there's interesting things that happen when a gets really big and x is really small, but having to do with the number e. But really, this is the case that pops up often. This is a case that we're interested in right now. This is called the binomial. So this whole thing is called the binomial series expansion. So for that particular choice of function. Okay, and again, for emphasis, I'm just going to write this down one more time because you will need this over and over again. This is about equal to 1 plus a times x. So just imagine you can take this down and multiply it there. Just as long as you realize that it's an approximation. So there are more terms here, but if a times x is small, you're ignoring terms that are really small compared to a times x. So this winds up being an okay approximation. Okay, let's see how this works out for our original problem. Okay, if you were to increase your distance to the center of the Earth by 0.10%, and we're asked about the weight. Okay, let's see here. So your weight is mg, right? But this is not allowing for variances in the distance that you are from the center of the Earth. So weight equals mg, right? Well, this is true, but we want to know a pretty fine detail, a relatively fine detail. So it's true that weight is mg, but if you were going to say weight equals mg, m doesn't change, g doesn't change, then you're saying that the weight, the gravitational force, is the same no matter how far you are away from the center of the Earth. So this is too big an approximation. This corresponds to the 0th order approximation here. So this is true but not accurate enough. True, but we want more info. So this is approximately true. But we want more info. We want to know roughly like how much it's going to change. So in other words, like this, if x is small, 1 plus x to the a is approximately equal to 1, right? You could always say that and that would be true. But the point of using this is that we want a little bit more information than that. We want to see how it changes, but we're not interested in the exact value because doing this can be complicated. So you're going to see this over and over again in physics, but it's going to involve complicated functions that you can't evaluate easily exactly. So this approximation comes in handy and it simplifies expressions. Okay, so how is this going to arise? So the gravitational force, it's equal to mg. That's a good approximation, but we have a more exact expression for this. This is the magnitude of this is g, mass of the Earth, times mass of the object, divided by r squared. Okay, so I'm going to plug in, so g m1, m2 over, I'm going to plug in for the distance that we are to the center of the Earth. I'm going to plug in the radius of the Earth plus some height that we are above the center of the Earth, squared. Now this doesn't at all look like our binomial series expansion, right? But it is actually. And let me show you how this arises. Okay, so we're going to look at this in the limit where h is much, much less than r. So see how we're going to an elevation here, 4 miles. So we're going to increase our distance to the center of the Earth. We're going to go to a height that's 4 miles up, which is much less than the radius of the Earth. Okay, so like the x in our series expansion is going to wind up being h over r. So in other words, h over r is much, much less than 1. Okay, so let me rewrite this in a way that's a little more suggestive. So g m1 m2 over r squared. So I'm going to factor out an r squared from the denominator here. So this is 1 plus h over r squared. And even more suggestively, g m1 m2 over r squared times 1 plus x to the minus 2, where x is h over r, which is much, much less than 1. So this is perfect, right? This is exactly written in the way that we can use our binomial series expansion. So this is approximately equal to, and this is the step where we're using our binomial series expansion. 1, and remember we could just take this and multiply right there. So 1 minus 2x. Okay. So the gravitational force, so if x is 0, we're at the radius of the Earth. We're at h equals 0. That's where, so the gravitational force would be this, gm1 m2 over r squared, and then we would just multiply by 1 if x was 0. So 2x is the fractional decrease in the gravitational force. Okay, so what this is saying, so reading this, interpreting this equation, this is saying that 2x is the fractional decrease in the gravitational force. So in our problem, we were told that we increase our distance to the center of the Earth by 0.10%. So what that's saying is that h over r is 0.10%, or in terms of a fraction, it's this. This is 0.10%. So our x value, h over r, is 0.10%. And this means that our weight has decreased by, it looks like 2x, right? So this tells us our weight decreases by 2x by 0.20%. And that's our final answer. So notice how we didn't have to plug. So another way you could do this, and you might want to double check our answer by doing this. You might want to double check, like plug in, so weight equals mg, and g equals g capital M over r squared. So you could take that value, plug in g, plug in the mass of the Earth, and plug in two different values of r, plug in the radius of the Earth, and find out the value of g. You'll get 9.81, 9.82 meters per second squared or something like that. And then plug in not the radius of the Earth, but the radius of the Earth plus this 4 miles, 4.0 miles, or increase that value by 0.1%. And then find the new value of g. And you'll find that it goes down by 0.20%, or something very close to that. Remember, it's not exact because there's more terms here. There's a order x squared term. There's a plus something times x squared term here that we forgot, or that we didn't include. But it's going to be very close, and you can see with your calculator just how close we're going to be with this approximation. Okay. Okay, we're now to the final part of the video where, so we saw how the binomial series could apply to forces, but now we're gonna be interested in energies. Okay, now finally going back to Shankar here. So we have the potential energy as a function of r, and this is the exact expression. Remember, we're taking the exact expression and then deriving an approximate expression from that. So we have u of r is minus g m1 m2 over r. And that's true no matter the distance, the center to center distance of the two masses. And that's exact. So let's plug in. Let's take that the distance that we are to the center of the Earth, it's basically the radius of the Earth, and then we can allow for small variations. So maybe we're a few meters off the ground or something, right? That's the way we were using MGH. We were just looking at 10 meters, 100 meters, etc., but a small number compared to the radius of the Earth. Okay, so let's plug it in. So we have u of h now. So now this is, this is the variable, lowercase r. We're writing that variable as this constant plus, and then now this is the thing that we're imagining could vary, right? Your lowercase m, it can change its height, but we're not going to change the radius of the Earth. So we're changing variables from lowercase r to h, the height above the Earth's surface. Okay, so that's why I wrote u as a function of h right here. So u of h is minus g m1 m2 over r plus h. Okay, so again, this doesn't look exactly like the binomial series expansion, but we can rewrite it in a way that's more suggestive, just like with that example problem. So let's do that. So, so I'm going to factor out a capital R, g m1 m2 over r. Actually, let me rewrite this. Maybe it's not clear what I'm doing. Let me factor out an r, so this is 1 plus h over r. And now I'll write it like this. So this is clearly a constant. And then we have 1 plus h over r to the minus 1 power. Now this is exactly our binomial series. It's written in a way that we can use the binomial series expansion. Right? And again, it's just bring the exponent down, multiply right there. So this is approximately equal to, and this is true in the limit that, so this is a good approximation if h over r is much, much less than 1. So the formula that we derive will be okay. It will be a good formula as long as h is small compared to the radius of the Earth. Okay, so whatever we write down following this, if h is equal to the radius of the Earth, it wouldn't be good because we're using this approximation right here. Okay, so this is equal to, so I'm just copying down this constant, and now I'm going to apply our approximation says 1 minus h over r, and then there's more stuff that we're going to throw away. Okay, there's something times h over r in parentheses squared. But if h over r is small, then when you square it, it becomes really, really, really small. So we can ignore it compared to this term. So these terms get really a lot smaller. So if this term is 1 and this term is like 1%, this is going to be 1% squared, or 0.01 squared, which is 10 to the minus 4. So it's going to be really small compared to this second term. Okay, so this is minus gmm over r plus gmm over r squared times h. And let me remind you here at this point that g, so maybe going back to this right here is what we call g. You know, the 9.8 meters per second squared. If you, oh shoot, actually it's with the radius of the Earth that it would be equal to g. So this right here is g. Looks like a little heart. We use it so much that I put a heart there. So if you plug in Newton's So the gravitational constant here, the mass of the Earth, the radius of the Earth, you'll get 9.8 meters per second squared. That's g. So gm over r squared, so right here, this piece right here is g. So this is equal to a constant. So all this stuff is constant. We're just saying that lowercase h can change, right, with our potential energy function. So we have a constant plus, see what's left? We have m, g, h. m, g, h. And then there's other terms here. But this is exactly where mgh comes from. So we have the exact expression. If we look at points near the Earth's surface, the potential energy is a constant plus mgh is the main way that this expression changes for points near the Earth's surface. And then there are smaller terms that are very, very small compared to mgh, and so we don't have to care about them. So when we do like conservation of energy problems, where potential energy is converted to kinetic energy, we just care about changes in energy. And so this is the point that your book makes. Choosing the constant in U is the title of this section. So in other words, we can just kind of ignore this constant, because in any physical problem, you just look at changes in potential energy. You can't measure absolute potential energy. It's always potential energy relative to some other configuration. So for points, so the conclusion here, with a different constant, we can choose our potential energy function to be mgh. With a different constant from our normal potential energy function so with a different constant from u of r is minus g m1 m2 over r, we can choose this to be our potential energy function only if we're sticking to points near the Earth's surface. Okay, so in other words, this section is justifying why we could use mgh, or they might call it mgy, why we could use mgy in previous sections, like when we were doing conservation of energy problems. Okay, so this is not the last time you'll see binomial series, so it's good we went over it in some detail. And then the rest of the section we covered in a previous video with escape velocity. All right, great.